So with that, I will start the Jitu. I will call you Jitu. Nice name. So would you please put over the presentation now?
Yeah, okay, sir. I'll just share that. And with that, let me just tell you, everyone, whatever the doubt you are having throughout the session, just put in the chat box. Okay, we'll cover all those doubts in the end, and there will be the interactive parts of the whole session. Okay, as it always happen. Okay, so just don't worry about that again. Okay, so yeah, sir, we are all set to.
Yeah. I hope the screen is now visible to all our people. So I'll try to explain each of the paras and add a few words to each of these paras which I have written. So ISRO initially started way back in 1962 in what used to be called the INCOSPAR, that is the Indian National Committee for Space Research. It was established under the Atomic Energy Department, actually under the atomic energy itself. Subsequently, the Indian Space Research Organization was becoming an independent entity in August 1969. This year it was celebrated, last year it was celebrated as the 55th year, and it was done in a very nice way. In place of INCOSPAR, it was done. Finally, at this time, it was still what is called a non-governmental organization. In 1972, the government of India decided that the space activity was too important, and it decided to constitute a space commission and establish the Department of Space. And ISRO, Indian Space Research Organization, was brought under the entire umbrella of Department of Space. So here the important point for all the young people as well as old people to remember is that finally I am a retired government officer. I worked with the Department of Space, Central Government of India, and ISRO, even though it is a technology, a spearhead type of organization, it is actually one of the departments of the same Government of India that we all work with every day. So to concentrate on today's subject, I'll be talking on the ISRO programs and projects for Earth observation. The very first one was the experimental Bhaskara 1 and Bhaskara 2, which started 1979 was the first launch and 71 was the second one. These launches were carried out from the then USSR, United Soviet Republic. And these were hosting in those days not the type of sensors which we use today. Those days, the CCTV, CMOS detector, CCD detector were not present at all in the world, or even if they were not accessible to all. We had put the television cameras, and these were scanning the Earth in 0.6 microns and the near infrared 0.8 microns. And with this, they started the actual Indian remote sensing program. This was the first time that India started developing a satellite called, and it was named Bhaskara after our Bhaskaracharya. The first satellite we made was called Aryabhatta after Aryabhattacharya. The second set of satellites we made were Bhaskara after Bhaskaracharya. Then followed the pioneering IRS-1A and IRS-1B, which started the basic program, which is now known as the Indian Remote Sensing Program, and the INSAT Meteorological Satellite and Payload Series. These are now considered as one of the, amongst all the spacefaring nations of the world, these two programs, Indian Remote Sensing Program, Indian Meteorological Satellite Program, INSAT program, these two programs are considered one of the serious standards and are used across the world in terms of their data, both in terms of quality. And I will be also showing you our very, very reputed organizations across the world hosting our data as well as speaking very nicely about it. So now this huge chart which shows here is showing from our website all the satellites which have been launched for Earth observation, starting from Bhaskara 1 and Bhaskara 2 on the right bottom corner and going up. 18th is the second side, right side. I actually cut and pasted this from our website, and these are all published information. This is updated till 2018. 2018 is CARTO 2 series. the Kato 2 series actually, and then onwards there was Kato 3 series as well as the Ocean Sat and Resource Sat extra series have come up. So you can see that it's a huge volume of satellites which have been put, and this has been one of the very major programs of Indian Space Research Organization. This information is also available on some of the ISRO websites and pages. At a later time, if people have deeper interest, you can get back to me. I'll be able to answer it. Now, in terms of this is the basic Google info and is hosted both by Wikipedia as well as the United States NASA sources. Leading agencies and programs published web info. Here, ISRO has one of the largest constellation of remote sensing satellites used for various applications, including disaster management, urban planning, and water resources. And so basically, we stand in the few set of nations across the world which has one of the largest set of constellations of remote sensing satellites. Basically, remote sensing is Earth observation satellites. And by observation, we here mean not taking a photo, but by actually measuring the parameters which are reflected back to the satellite. So now, what exactly is satellite Earth observation? That's basically coming to the basics. So satellite observation is the process of collecting information about the Earth's surface, ocean, and atmosphere using remote sensing satellites which are equipped with sensors or cameras. How this is done? Basically, the sun is illuminating the Earth, and the Earth itself is also giving out what is called the long wave radiation. At night, we are able to see the Earth in the infrared channel, and these are what is called the outward long wave radiation. Okay, so the Earth itself getting heated up, it sends up the heat signals. During the morning, we get what is called the albedo reflected at the top of the atmosphere. The part of the light which goes through the atmosphere to outer space back from the Earth. A very famous part of this is what is called the blue Earth, the blue marble photo, which creates the what we call color photo of the Earth. That itself shows that the Earth is visible from outside. And these sensors, they are mounted on a spacecraft or satellite, and we have find out for the applications for weather forecasting, climate change, disaster, urban planning, and resource management. At the time of 1980s, this used to be still very novel programs actually, but now these are part of our life. I'll be showing you subsequently. As a matter of fact, you may be surprised to note that every day when you see Google Maps, just try to see at the bottom from where they got the data. They will be telling you they got the data from a European satellite or from an Indian satellite or from a NASA satellite or from a Japanese satellite, and they will tell you the date and time at which the images were taken. So whether it is Google Maps or not, day to day, whether it is a flood mapping, whether it is finding out whether crops are good or not, whether the water is there in the land or not, whether there is too much of heat in the atmosphere or not, everything is now monitored by satellites. The advantage of satellite platforms is that once you put a satellite on and it works, it may work for several years together and go on working. Yeah, there is some comment. Okay. Now you continue with the first page itself. Yeah, first page itself. Yeah, please. So this consists of the sensors, then the imagery and the data which they collect, imagery and the data which they are collecting. After that, the data has to be transmitted back to the Earth. Then we have to process the data. Raw data from sensors is processed using useful information such as maps using land surface, temperature mapping, etc. So this is basic theory of remote sensing as Earth observation. The types of satellites are geostationary satellites, which are always locked in orbit with the Earth's rotation. So if the Earth is orbiting exactly 23 hours, 59 minutes, then we are also orbiting exactly at the same time. So they maintain their position with respect to the Earth's location which they are. If a satellite is at 74-degree latitude and over the equator, it will remain exactly over there for its entire lifetime. It has to be forcibly kept there as well. Then low Earth satellites, these are actually what we call the smaller satellites and some special purpose satellites, mostly sometimes for military purposes or something like that. and used more for identification, not for measurement. And the major part of Earth observation consists of the polar suns or synchronous satellites. These are all the satellites which I showed on the first set actually. So whether we call the INSATs, the IRS series, the Cartosat series, ResourceSat series, OceanSat series, all are polar sun synchronous satellites, which I'll try to explain that what is polar orbiting sun synchronous satellite. And as I come to one of the examples, I will actually do it. I think we can go to second page now. Major applications. Yeah, so the major applications of the electro-optical satellites as well as the Earth observation satellites has a vast array of applications across all fields, starting with what is in thing nowadays is climate change. Everybody talks of climate change, environmental monitoring. This includes long-term electro-optical data or Earth observation data is critical for tracking global warming, rising sea level. More important thing is ozone depletion. It's also used for monitoring deforestation. Why this is important is because the satellites go on taking images over years and years together. It creates a historical record of what is going on the Earth's surface and how the things are actually coming around, how they are changing, whether any deforestation is happening, whether somebody has added new plants and new forests have been planted, whether the polar ice cap is melting or not, whether the polar ice cap has increased or not. Then rising sea levels. Rising sea levels, for example, is found out by finding the low-lying areas around the land borders. So let us say certain mangroves are there. Whether the waters of the sea has now ingressed inside the land more where compared to let us say 1985 or 1995. So this gives a idea about whether the sea level is rising or shrinking. So these are one of the applications. Then disaster management, for example, very recently all the type of flash floods which have occurred in the Himalayas, as well as the floods which have occurred on account of the opening of the dams, they have been mapped properly, and sometimes very quickly they have been notified that this is where the NDRF, National Disaster Management Force, has to be sent, and the satellites were nearly in near real time in India itself, and this is so in all other countries as well. Then comes weather forecasting. This is one of the very large areas. Any one of you can see the India Meteorology website and you will keep seeing the satellite images. We now generate as many as 48 images per day, every half an hour, and we keep on generating 2 images actually. So there are n number of images available which now provide nearly what is called forecasting as well as nowcasting. And every day the satellite meteorology has actually improved the weather systems, and India is amongst the very few countries which has a meteorological satellite which is geostationary and keeps on providing data continuously. Agricultural forestry application, this is most important for our farmers because when to sow the crops, when to harvest it, whether any uh, pathogens, that is any uh, the spoilage of the crop is there or not, browning is there or not, if the greening is loss is there or not, then similarly whether there is a water logging or not, all these type of things including the insurance claims of the farmers, they are also now tracked by the insurance companies using the satellite data. Urban planning is most important, especially with what is called the cadastral mapping satellites, which tell the people as well as that where the land is available or which part of the land is having what type of alignment. So these are the urban heat islands. So for example, which part is likely to be, which should be developed in such a way to provide a normal passage of air and everything like that. So these are all the things which is providing satellite data. Resource mapping, whether our dams are getting filled or not. Fisheries monitoring is one of the very great areas where we can even find out where the plankton is, where the fish will be. There is a OceanSat series of satellites which we have developed which is exclusively for the fisheries. And similarly, whether the siltation from the rivers is going on in a higher order or lesser order or something like that. Mineral prospecting is, however, restricted to the surface of the reflected light only, but still is useful in uncovered areas so far. Now we will go over to some of the examples, the beginnings, how it started in ISRO. Uh, yeah, this slide is very nice. Okay. So Bhaskara 1 and Bhaskara 2 were what was called the harbinger, or the starting, the beginnings of it. We just started it actually. And these were the very experimental in nature in those days. This was developed in the late 1970s and launched in first in 1981. And in those days we didn't have our launcher, so they were launched from the web, from the place called Rapsutin Yar, that is in USSR. And Bhaskara 2 was also launched in 1982-81. These were having the very high voltage 12 kilovolt and very high voltage type of television cameras. You see, you need an actual TV tube, Vidicon tube it is to be called. And it was very difficult to make this in those days, to seal it and all types of things. But still, the Bhaskara 2 was able to generate more than 2000 images. I could collect one image which was good from somewhere. And this was the first time that we actually carried out the entire what is called the camera. You have to understand that the camera is always made at Space Application Center, Ahmedabad. All Indian satellites application part, antennas, cameras, these are all made at the Space Application Center, Ahmedabad. The satellites are made in Bangalore, and the rockets and everything are made at VSSC. And the launch comes from Sriharikota. So the first time it was ruggedized against corona. What I said, corona in space, which means that there is a discharge in space which can happen in vacuum. So that was discharged. So it was a very difficult technology, considering that very little technology was actually accessible to India in 1970s. Despite the problems faced by one of the two onboard cameras of Bhaskara 2, it sent down more than 2000 images which were used for study. So this was the beginning and the starting of what to do with all this data, how to do with that data, and how we should go about it. So this one image it shows a ice cover near the Himalayas actually. One of the images is available. And these are the specifications taken from our website. And this is how the Bhaskara satellite used to actually look like. There are postcards and post stamps were also made on Bhaskara actually. So it used to weigh 444 kilograms. One important point I will tell you is Bhaskara was spin stabilized. Spin stabilized means that the axis of rotation, it will go on rotating. And while rotating, the scan happens. The camera moves in the ground direction and goes on scanning. After this, we went over to what is called 3-axis stabilization, which means that like a human being is standing, the satellite is also standing in space. Then we will go over to the next slide now. We are now talking of the IRS 1A and 1B. So IRS 1A and 1B were the two satellites of a series which had actually 12 total cameras, 8 which were of the higher resolution combined together, and 4 which were of the lower resolution. That is, the lower one resolution is 72 meters and 36 meters is the higher resolution. From space, when you see the Earth and the resolution doubles, you actually need double the amount of cameras. It's the area wise. So it becomes, resolution actually becomes 4 times. 36 meter means to cover a 72 meter by 72 meter square, you actually require 4 pixels. You require 4 pixels of 36 meter by 36 meter. You have to understand that. This is similarly like a telescope. The steradian angle increases as the square of the area. So you require double the number of cameras to cover it, and with the double the number of swath which actually covers. So these were the first two, you may say, the cameras or which we were created by ISRO. And this was a very courageous step. For the first time, we made use of linear imaging self-scanning. I'll explain what is the technology, linear imaging self-scanning. And these were launched in March 88 and August 91. Let me tell you that they worked for a very long time, almost 8-9 years, and they went on sending the images. So it was a part operational, part experimental mission to develop Indian expertise, and then started the series of operational electro-optical, spelling mistake kar diya maine, remote sensing passive followed by microwave sensors active. So this is a artist impression of the satellite. I'll here explain the basic satellite. On the right side photo, you have what is called the satellite actually. The blue ones are the solar panel. The main body, which is slightly larger, hexagonal, the square, that is actually the satellite body. On top of it are mounted, you can see the 12 small figures which can be seen. The middle one is actually the 4, what we call the LIS 1, that is the lower resolution. and the outer two are the least two, which are the higher resolution. And the four cameras are seen here. These are, as you are seeing, these are the 1980s technology. So 1980s technology, if you see in detail, those who are engineers here or those who are technologists, they will realize that we are making use of still what is called the RSD type of connectors, 9-pin connectors, 25-pin D type of connectors, even though these D type of connectors were actually military grade and space grade. The colors which you see on the top of the camera, they are actually the reflecting colors. So if you see green color, it means that it is reflecting green light, but it is allowing all the other bands inside. The red color means it is allowing all the other bands other than the red inside. So these are the reflecting filters actually. So this is the idea. A good image which was available, I have shown here. This is of the Himalayan region, which shows our sub-Himalayan region, and the water flows are the blue. The red is actually the green area, and this is called a false color composite. So a bit of knowledge on this. A bit of knowledge on this again from what is called what is a false color composite. When you see a satellite image, the red channel is actually assigned to near infrared. Green channel is assigned to red band. Blue channel in the photo is assigned to the green band. And as a result, what you get is actually a false color composite. So the real color composite, I will also show later on a real color, what is called the near true color. This is a false color composite by mapping each band, which means that the satellite does not exactly see the same way as our human eye does. It has a wider bandwidth and different type of cameras with a different type of filters. We can go to the next page. So this is describing what is called how a linear CCD takes the images. You have to understand that the spacecraft is actually in orbit, and in general the polar sun synchronous satellites, they generally move between somewhere between 6 to 7.5 kilometers per second, which means about 6,000 plus kilometers per second to 7,500 meters per second. So if you want to take the images, first and foremost, depending on the resolution, for example, a 10-meter resolution image, if you want 10 meters, each pixel is 10 meters. So the actual time which the satellite will give for viewing will be at 7,000 meters per second only as low as 10 upon 7,000 meters. Understood? So by that time, the satellite has moved forward. So the very fast systems are required, and hence this method is considered. So this linear imaging self-scanning scanner, the scan is actually along the swath of the movement. And this is also called the push broom, because it's like a broom being pushed forward. It's like a broom being pushed forward. So the image keeps coming in terms of what is called the swath. The swath which is shown, the right to left, that is actually the view angle of the conical view angle, which it will view, and only the center part it will be imaging, even though the entire circle will be imaged. This is the basic method of any LIS camera, and this is the standard method used across the world for all CCD based sensors. We can go to the next slide. Now I am jumping from the 80s back straight to the 2000 AD, and instead of quoting a ISRO website, I am straight away quoting here the United States Geological Services. So why I am quoting that also I will tell you. You see, the United States Geological Services is one of the most reputed science and technology organizations in the world, and that organization accepting and hosting USGS website. ठीक है, यही रखिए. The accepting and hosting Indian resource sat and other satellite data, it's a matter of happiness as well as the fact that we can actually do it the same way as they also can do it. So some people go on saying कि हम लोग नासा से सीख के आके इसरो को सिखाएंगे, मगर ऐसा जरूरी नहीं है. हम लोग जो करते हैं वो भी यूएसए का डेटा यूएसए में ये होस्ट किया जा रहा है. And most importantly, I want to tell you is that the data being hosted is over United States of America, which means that our satellite has viewed USA and they are responsible for this data. A United States government does not host any data if it is not cleared by it from both quality control as well as accuracy control. But in spite of that, they have hosted it. The details they have put on this website: multispectral imager, 24-meter resolution, 56-meter is advanced wide field sensor meter data. And some of the pages you can see they have given the details also. I have taken screenshots from their website and put it to tell you that the USGS hosts the ISRO data, and that itself is a plus mark for the quality of the satellites and the sensors we made. So they have a huge archive, and surprisingly, they provide this data free of cost. We can go to the next slide. Yeah. So see, and they have described our satellite in a very nice manner, which you can see. Every detail is put over here, which will tell you exactly how it is done. So ResourceSat 1, our designation was IRS-P6. ResourceSat 2 is the general name which is given. We are scanning in 4 spectral bands ranging from visible and near infrared and shortwave infrared as well. This is very difficult to create, and the sensors are also denied to us, but we were able to somehow get it. And from an altitude of 817 kilometers, every nth day it will go on visiting. Every 5th day there is a revisit. 101 minutes is the orbital period, which means that after 101 minutes it will revisit, start a next orbit, which is exactly 14 orbits it will complete per day at 101 minutes, and it will take 14 slices of the Earth view continuously per day. In those days, we did not have what is called the SSR, solid state recorder. So these type of satellites needed ground stations to directly download the data. That is more important. So the LIS 3 sensor covers 140 kilometers, and this is useful for all types of agricultural mapping, mineral mapping, then water body mapping, so shoreline mapping, then the overall what we call the urban sprawl mapping, and it has proved to be very useful. And there is a series of satellites. As a matter of fact, ResourceSat 3 has been also launched, and they are also receiving such data. I think we can go to the next slide. So what type of processing they are doing and the details of the satellite, that they have put out so nicely on their own website, exactly in the same way as we do it actually. So which is the spectral band? 2 micrometers. Okay. So 2 micrometers wide is the AWIFS band, and then LIS 3 band 0.52 to 0.59 is the micrometer range, that is green color. Then 0.62 to 0.68, or what we call 620 nanometers and 680 nanometers, that is our red range. This is actually mapped to our own eye color. Then near infrared is not visible to our eyes. We can see only up to about 0.73. So 0.77 to 0.86 is the NIR. Some of those who are astronomers here, they would be aware that some sensors are available in certain cameras which actually see near infrared by removing the filter on the sensor. But these type of sensors are LIS sensors, which is a line sensor actually, and they are specially made for these bands. SWIR is a separate sensor. It is called the shortwave infrared, and for this mapping we can get also some information about the water vapor content in the soil, as well as water vapor content on the subsoil. So the swath was 740 kilometers for the AWIPS and 140 kilometers for this, and this was hosted. This entire information about ResourceSat is hosted on the USGS website. So the point is that United States Earth Resource Observation Science Center processes all ISRO data of IRS-1G. It's not that India only uses the data, it's a worldwide data. And it is hosting as per the special format, georeference tag file format, that they are hosting it up to WGS 48. That is the specifics of the details of remote sensing community are aware of this actually. So just to tell you that the satellites which we made are actually made available to the general public of USA also, and it is a credible thing what we did. Now this is a photo of the ResourceSat 3 LIS EOM camera. There is the higher resolution camera actually. Now here one thing very interesting for all those who are listening. Just see the, can we go to the next slide? Yeah, we can skip this now. Yeah, this one, yes. So here on the top photo, this is that insight is what is important. Okay. First and foremost, these are the 4 different cameras which are actually seeing with the different bands. That is one thing. One of them is the SWIR band, which will be actually reflecting the red light. Actually, the red light is being reflected. So these are the 4 bands which are seeing it. On the left side, on the black box, you are seeing the D-type connectors. In those days, we were still having the D type connectors. Now I think we have replaced them with better connectors. You can see that the wires are actually tightened together so that they don't fall off when the satellite is being launched and actually is in space. These type of connectors in electronics are very special in nature actually, and they are such that they don't burst in space. That is, outgassing has to be done. Wires are also of a very special type, and these wires are coming from what is called the detector handling unit. Okay, but what I want you to focus on is those dots on the table which you are seeing. This table we are still not able to make in India. We can make the payload, we can make the satellite. This table, which is a precision, those each dot is accurately what you call screw threaded dowel threads are there, and they are so accurately placed. These are made in from foreign companies. We have to buy them. That's a special table which is mounted on a pneumatic mounts foot so that it does not vibrate. It's called a vibration isolation table. And on this, the optical workbench, that table itself is the optical workbench. Some of you who are with the Indian Institute of Technology or Indian Institute of Science, they may have seen such things at that places also. The very costly piece of equipment, that table itself. And those, the dowel screws which are at so accurate distances that if you move, the very accurate measurement of where our sensor has been placed on the table and how we are actually testing, it can be done only on this table. Now this is an image which is different from the false color composite. In this image, we are seeing what is called the near real color, which means the green is mapped to green, water is mapped to blue, ice part is mapped to white, the Tibet part on the north. This is actually the white part is entire Himalayan region. The river which you can see is actually the Ganga river. Then there is the Brahmaputra river, and then finally the Padma river, and the most important thing is the color coding which you can see of the siltation which has happened in the Bay of Bengal. So the 24 Parganas as well as the siltation which is happening both on the Bangladesh side as well as the Hooghly side, which can be seen very clearly. Some of the reservoirs of our dams are also seen. And the green which you are seeing are actually the forested areas in the Odisha and the Jharkhand and Bihar region. So this is actually a very compressed small map which I have taken. The actual map is several thousands of pixels big, and it is several kilometers, hundreds of thousands of kilometers merged map actually. Very detailed photographs are generated of the earth regularly, from which our resource management is carried out. I think we can go to next slide now. So now I am going over from the resource management and medium resolution sensors to the Cartosat series actually. What is the time? 1944. Okay, fine. Fine, no problem. Cartosat series is what is called the high resolution series which ISRO created. And obviously Carto name itself, Carto name itself means that you are going for cartography. So cartography requires a high resolution, and the thrust on this is more on the panchromatic side, which should be able to identify the objects. The photograph here which you are seeing is actually more or less like a 3D CAD drawing from which it has been taken. The central portion which you are seeing, the magenta color, that is the actual camera. That is the actual camera, and the plus your direction which is written will be actually the earth view and the camera. So in this type of Cartosat series, these were what is called the agile cameras, agile satellites. They were made very lighter, and I will explain also that why they were made lighter actually, because these are the first series of satellites which were developed, Carto 1, Carto 2, and now then later on Carto 3, wherein the satellite itself can be pointed to the direction where the imagery has to be taken. So it had a special facility for pointing. And additionally, now I'll describe what sort of sophistication or the complexity exists in this satellite. The two sides blue which you are seeing, they are the solar panels which will generate the power. And these are also what we call mounted on special points which are called the SADA, Solar Array Deployment Assembly. They will keep on rotating and always pointing to the sun. So 4 pi sun sensor hai. Sun sensor will actually orient the satellite, then the earth sensor will be there, and star sensor is there. So this is for the orientation of the satellite accurately, which is very, very important. Alignment of the satellite as you go for higher and higher accuracy of imaging on earth. So Carto 2 series itself is a 1 meter resolution image. It's a challenge to image 1 meter from 700 plus kilometers for every nation. And for India, it is a much bigger challenge because these are all what comes under the category of denied technologies. So every nut bolt screw भी आपको खुद बनाने का है और कोई आपको टेंडरिंग करके कोई देने वाला नहीं है. बना सके तो बनाओ, नहीं बना सके तो नहीं बनेगा, बस ऐसा ही है. मगर फिर भी किसी तरह से इसरो बनाती रहती है. और ये एक it's some people have told me when I talk with some people from outside that you people are enigma. So somehow, but we still are able to do it, and it happens. The one important thing which I want to tell you is that electronics in India, in terms of actual components, is still in a very nascent stage of manufacturing, especially the type of satellite components. So the core ICs, other than now the one of the CPUs or few of the ICs which we talk of, like the Vikram processor, which has been developed, CPU, for example, has been developed since a long time. It was developed over here, and now it is actually getting fabricated. Some of the detectors for our Chandrayana were once fabricated in our semiconductor complex, Chandigarh. But other than that, most of the ICs, what we call, and the chips, etc., these still have to be, raw materials have to be imported. But that apart, the cost of such thing is actually very small compared to any satellite put together. So here we are able to see actually the overall structure of the satellite. It's a cuboid type of structure, hexagonal structure. The yaw plus direction is actually pointing down to the earth, and the pitch direction. In terms of satellites, we have three directions. We call it the roll, pitch, and yaw direction. The direction from the earth nadir view to the null, that is space view, is called yaw. The direction travel of the satellite is called the roll direction. And this comes from the shipping technology, actually the same as what the ship is. If the ship is moving sideways, then it is rolling. If it is moving forward and backward, it is pitching. So the same way the satellite roll, pitch, and yaw directions are always there. And these are the actual components of the satellite. If we go for a more detailed discussion, someday I will describe each one of these. So this is a block diagram. Now we can go as a higher resolution, 1 meter or better, detailed remote sensing and mapping. Now I will show certain images taken by this satellite. This image is what is called a merged image. Now, what is a merged image, that I will tell you. The below one black and white is actually the very high resolution panchromatic. But the merged image is actually created by getting the color from the MX or the multispectral camera and putting the same color, that is overlaying those colors on the high resolution image with a image processing where it is the fractional pixels are actually rounded off or accurately displayed on the screen. So this is a part of somewhere in India actually. No, sorry, this is somewhere actually a part of Europe in those days. And this photograph is there. So this satellite actually had what is called as solid state recorders. So you can take photographs anywhere on the earth and download them back again wherever you like. You see the accuracy of the satellite from 700 kilometers. You can see the cars which are moving on the road. This photograph itself is road resolution. The actual resolution was very high. You can actually see which type of brand of the car it is, whether it is a long Mercedes or a small auto rickshaw or something, that also can be made out. Okay, then certain photographs showing our capability to take photographs of other countries. So Cartosat pan image from Alexandria, Egypt. You can see the accuracy with which the fields have been mapped, the different type of structures which are there, round structure. These are the fields are there within it, and they have done this type of thing. The canals are actually showing very clearly. And the lower image of Doha, which is a very famous image, is displayed on the ISRO website also. So this is actually Doha, where the water has been brought in and they have carried out construction on the shoreline. So these are showing you the high resolution capability. Now we are going over to the next slide. Now I change track to the geostationary imaging. So far we were discussing the polar orbiting 700, 800 kilometer type of high resolution satellites. Now for geostationary, I am starting with something again from a foreign website, and this is actually a worldwide website called OSCAR. This is WMO, World Meteorology Organization. Now, whereas it is showing the entire series, what makes me very happy is this word from satellite details. The first line is insert 3DS, followed by full name Indian National Satellite, second repeat, then World IGOS, that is satellite identification. Its ID has been given. The satellite description. What makes me very happy is this word, operational meteorology. You have to understand that very few countries in the world have operational meteorology satellites. the a World Meteorology Organization accepting that India has a satellite which is operational meteorology, which means that you are assuring somebody. जैसे आप ट्रेन की टिकट लेते हैं तो ट्रेन की टिकट आपका ट्रेन आप एक्सपेक्ट करते हैं कि 8 बजे की ट्रेन है तो 8 बजे चलेगी. उसी तरह से दिस सैटेलाइट इज एक्सपेक्टेड टू गिव इमेजेस रेगुलरली एंड सपोर्ट आवर कंट्रीज मेट्रोलॉजी एंड आवर वे ऑफ लाइफ in a correct way, that even the foreign countries, that is the world organization, is accepting it out. So what it is doing, that is, they have described it in detail. I will actually now come to the type of sensors which are used, and mainly the imager and the sounder sensor. You can actually see the images from imager and sounder regularly on the IMD website, because they are putting it out on regularly. Every half an hour they will be going on updating it. So this I have captured today's images itself at 17 hours, that is 5 o'clock to 5:27. And this is the infrared image. The other one is the visible image. You can see the fascinating thing that the earth has become dark on the eastern side and is still bright on the western side. So you can see Saudi Arabia, Iran, Caspian Sea, Africa's Horn of Africa, that is Ethiopia, and the corner showing the bright lights and the clouds on that side. India is slowly becoming dark. Okay, so this is the sector image actually taken from the imager, and the type of image processing which is done is not today's topic, so I will not cover it. And the fitting of the image is done is as per the Mercator projection. So the stretch is 0.5%, and the Mercator map projection has been fitted to the satellite image. The satellite images gives what is called the bird's eye view. In terms of bird's eye view, the projection will not be Mercator projection, so you have to remap each pixel back to the Mercator image. Then now I am trying to show here the actual engineering. So for those who are interested, they can later on get back to me. I'll briefly try to explain. Propagation, you don't have a time limit, na? Then I can continue slowly, or I will do it fast.
No, sir, there is no any time limit. You can take, sir.
Fine. So if the audience is interested, then fine. Let us continue. Okay. So this is actually the line diagram of a imager, INSAT 3D imager. The imager gives a 1 kilometer resolution visible, 1 kilometer resolution SWIR, and 1 kilometer resolution 3 bands which are NIR. The other bands are at a lower resolution actually. And here the challenge is that the infrared actually are maintained at a very low temperature. They are maintained at 70 degree Kelvin, that is 200 degrees, 204 degree, minus 204 degrees, minus 192. The range is from minus 190 to minus 210 degrees operating range. And I will show the structure also, which will tell you exactly how this is done. You have to understand that to cool anything in space, you don't have any table pankha, you don't have any conducting material. Everything is vacuum. So everything is radiated heat, and the only way to cool something is to throw the heat out to what is called null. So to the deep space. And that is itself a very difficult part of the job, thermal engineering in satellites. Now, as this is a geostationary satellite, it is not exactly scanning. You see, as it is not scanning, you have to create the scan. So in front of the telescope, because the low Earth orbit, they had the advantage. They were moving over the Earth. So the scanning was advantage. Here there is no movement, because it is simply looking down from the Earth down to the Earth continuously. So the detector array, either you put a very square large detector array and take the images, which is very difficult because all camera sensors or large arrays which we have, they have no sensitivity at this level. We require the very large photodiode arrays or the very large CCD arrays. So this type of photodiode arrays only can take the image, and they are actually in terms of several tens of microns in size. Our camera, especially let us say the so our cameras, we are having very small detectors. You see, if you see, they will tell you 1 by 2.33 inch sensor, and that is the diagonal size. Each pixel is 1 micrometer, 2.1 micrometer. Even the very large SLRs, they have actually sensors which are 5 micrometers, 4 micrometers. So they can trap the light only on the Earth surface. The satellite does not receive that much light. So we have to use a different type of stationary sensors. So for this, we have what is called the left side is the scan mirror. The left side, what you see is this is actually a special device which is turning from first east to west in approximately 1100 milliseconds. That is 1.1 second, which creates a east to west scan. And then it steps north to south direction every time. And that is how the entire INSAT image is created. And these mirrors are made of beryllium material or special aluminum or lithium material, and they have to be coated. The most important thing is this part is always exposed to deep space as well as to harsh sunlight. In spite of that, it has to work, and every one of these mirrors, they are made in India. They have worked for several tens of years and they have been successfully working. And the most important thing is this scan mechanism is operated by a series of stepper motors and an in-loop control system. It has to accurately move and step exactly the same, no overshoot, no undershoot, otherwise the image is gone bad. Then we have what is called the primary telescope. These were the 12-inch telescopes actually. And later on now, I think the next series is going to go for the even bigger telescopes. The secondary mirror, this is basically what you call a RC type of telescope, which is derived from your um, uh, Cassegrain type of telescope actually. The mid portion is evacuated, and this is, and as we have to have this type of folded telescopes in space. We can't have the earthbound Newtonian telescopes actually, because the length available and the size available of the entire chamber, this chamber is made of carbon fiber or it is made of Inconel, so that it does not expand at all. If it expands, then you can't do imaging at all correctly. Now you can see that there is a fold mirror on the right side, which is passing the band pass filter. These are actually the band pass and 3/4 filter, and the detector is there. Then we have a dichroic. This is a detailed engineering diagram. Dichroic means it will allow a certain portion of the wavelengths to pass through and the other portions it will reflect. They're generally gold foils actually. We used to manufacture once successfully, and it is still being done. Then the Sweer channel assembly, which is taking the light away on that side. Then again the 4 dichroics are there for the actually the MIR, water vapor band, TIR1, that is the higher energy TIR, and TIR2 is the lower energy TIR. This is up to 12.5 micrometers, and each one of them, the specifications you can either see from the website or I can get back to you. Most important thing here is the radiator window. These detectors are actually will not give you any image at all unless they are cold to this less than the liquid nitrogen temperature. On Earth, when we do the testing of this, we test them with liquid nitrogen type of temperatures. So we do get images on Earth itself from the infrared also, and they are tested at that time by putting a chamber which is very far away. You can't immerse them in liquid nitrogen, then everything kaput, khatam, finish हो जाएगा. वैसा नहीं करने का. इसको करके उसको बाद में फिर वैक्यूम करते हैं हम लोग. वैक्यूम करने के बाद इसको सैटेलाइट पे माउंट किया जाता है. Okay, so this is one detailed diagram which is showing you the line diagram of the imager instrument. Similarly, the more complex instrument is actually the sounder instrument. The sounder is used for atmospheric sounding by taking a different data of different bands, narrow bands. There is a properties, physical properties that, and these are all absorption bands, that they go on absorbing different type of radiations. And from those absorption bands and reflectance bands, one can make out the depth which goes, the depth of the atmosphere at which that image is there. And with the help of the sounder, we can find out the layers at which the wind is moving, as well as the properties, which are there of each layer, and how much is the density and all types of things like that. So for this, we have what is called the filter wheel. So this wheel goes on rotating. The wheel will go on rotating. I am talking of the one image on the lower one actually. That is the sounder instrument. The wheel goes on rotating, and there is a set of detectors which goes on sensing the wheel. The wheel is mounting the filters because these are having the 19 bands actually. Similarly, you have the scan mirror which has to go on scanning, and the same telescope is there with a very similar structure. And for a reference for the sounder, we always have a small similar 10 kilometer. This is a 10 kilometer sensor, a visible band which is used for the reference band. I think we'll go to the next. Yeah. Now this is a blowout of the entire instrument. It's an imager instrument which is a blowout actually. So here, as I was telling, that how to actually achieve it. So the one which is the plate which you are seeing is actually mounted on the plate. Inside you have the scan mechanism. What you see as a sunshade is actually the earth view. Earth view what you call canopy through which the additional light should not be able to get in, and the sun angle reflections or any specular reflections are to be avoided. This is specially designed keeping in mind the optics and the telescope size. The two bolts which you see, they are actually the rotating mechanism which I described, the scan mechanism and the scan mechanism electronics. So these the motion system, it rotates from the left to right, and it goes on, and plus it goes on stepping so that the telescope gets the data as was described in the line diagram. And later on, each of these from the telescope, we get the data back to the detectors, and the detectors we also have what is called the, here you will see the CEP, that is camera electronics package. The camera electronics package is actually mounted on this side. The electronics package will take all the signals, carry out first the analog to digital conversion, followed by the formatting, and then send it to what is called the baseband data handling system and onwards to the data transmitters. So now this is the entire detailed diagram, line diagram of the VHRR instrument. I could have shown actually, because such diagrams of the low earth sensors are generally not available in public domain. So these are actually available from some of our textbooks which have been published. So that's why I am showing this. If somebody is interested, we can have a one-on-one about the low earth orbit also, other than the Cartosat series. Cartosat is considered restricted technology. So here you see the entire what you call line diagram. I will here, the optical part I have already explained. So from here, as you see, this scan mechanism electronics is SME package. Then for everything, you need a DC-DC converter and regulator. So everything has to be operated in from the solar panel, the battery power, and battery power has to be regulated, and then it converts to DC-DC converter to all electronics. The HK processor or the housekeeping processor will give us the telemetry, whether our systems are working correctly or not, and the temperatures at each point, which are actually used for calibration of the sensor. And here you see what I was telling you, the infrared data as well as the visible data which goes to the video processor. This is the entire analog to digital converter. And after that, the entire data processing has to be done. On board, we have the formatter, and from formatter, it goes straight to main and redundant transmitter channels. The data from the imager is at 4 megabits per second. You will feel that ye kitna low data rate hai, but that's also a very high data rate for 36,700 kilometers. Okay, we can go to the next one. These are today's images, just for your reference. Yeah. So this is how a water vapor band actually looks like. So water vapor band is actually an absorption band. What you are seeing is bright over here. The image is actually inverted. Image is inverted. They will actually come in the satellite as dark, but the image is inverted. 1 minus x करके हम लोग display करते हैं. So you can see that near the 10 degrees south, there is some sort of a cyclonic formation forming. Then and the Danav type of photographs which you are seeing on the southern hemisphere, they are actually the water vapor high altitude. They show you the jet streams. So this is actually how the entire atmospheric dynamics happens. And if the meteorologists and even the person like me who has been seeing satellite photographs, we can tell from this what type of speed is there and what is there, everything. The white parts are the clouds which are there in the equatorial region, and the northern half is having too much of cold ice, cold water, and the jet streams are going on actually. So this is water vapor band and its utility. This is the full globe image. Then this is the thermal infrared, the next one. Okay. The thermal infrared is also, we invert it out. We have to understand. So the bright parts which you are seeing, they are actually the colder parts, and the actually bright what is seen in infrared, we actually convert it back to dark. So the hotter parts you will actually see as black, the colder parts you will see as white. So this is called the cloud top temperature. The colder, the more white a cloud is, it is the cooler, and the more black a land surface is, the hotter. So Saudi Arabia is very hot even at this night time. This image is taken at 17 hours to 17:27 hours Indian Standard Time. So, and you can see this is the image actually. So GMT time is also given here, 11:30 to 11:57 GMT time. So because GMT time is given, because this data is going worldwide to the WMO as well. Okay, so similarly, this is infrared. And the last one, एक page, यहाँ पे, हाँ, this page I had purposefully left out. So now I will shift from Earth observation to the Moon observation. I have already taken more than an hour. So I have a feeling that the audience is not leaving. So I think we can go over to Moon. So for Moon observation, I am going to cover today the uh, two things. That is the thematic mapping camera. This has proved to be one of the most useful cameras, not only for us to carry out the Chandrayaan 2 and Chandrayaan 3 and landing and everything, but also for the rest of the world, because this is one camera which it creates what is called the three-dimensional object images, even though it is of a medium resolution. So first of all, I am showing the line diagram in terms of engineering. That is how the Earth observation is happening. So, or rather in this case, the moon observation is happening. Let me tell you that the same TMC can work on Earth also. It's not that it cannot work. As a matter of fact, it may just, if we put it at 700 kilometers instead of this being put at about 150, it will give a lower resolution. Maybe we can make a bigger one also, but as of today, there is no plan to put it actually. So this was a unique design which was developed actually. And the focal plane is on this side. There are three sets of cameras. The lower photo will tell you the three cutouts which you are seeing. They are the three light entry points. There is a similar one on the other side. Okay. The box on the right which you see is the electronics box. And the inside what you see is actually the light which is actually focused through several sets of camera. The FM is actually the four mirrors. Aft is the aft mirrors. These are FM are the fold mirrors actually. So they will be folding. And these are very, very highly reflective creations of glass which are created. And these aft and similarly the mid view, that is simply nadir view. So three cameras look time to time on the same object. And this camera was mounted on both Chandrayaan 1, Chandrayaan 2. It was not there in Chandrayaan 3. And these were used for generating the DEM or digital elevation model. So how a digital elevation model is generated, that I will now show you. DEM, next screen, next slide. Yeah. So from this terrain mapping camera, DEM, from this is 2, that is from Chandrayaan 2. So altitude was 100 kilometers, sun elevation angle when the image was taken was 12 degrees. This is 12 degrees not on Earth, this is 12 degrees on moon. So you have the Smithson crater actually, four camera which I showed above. Then the nadir is the one which is looking down. The fore camera is looking front in the direction of the travel, and the aft camera is looking time. But the most important thing is each is going to cover the same object again and again from a different angle, and that is going to create effectively a stereogram type of thing, or from which you can create an ortho image. And from that ortho image, the color mapping is actually showing you the height. This color mapping is showing you the height, and from that you create the digital elevation map. You see, this is a 3D crater. The next one you are seeing below the color map is a 3D crater. Okay, so you can actually feel the perspective as well as the 3D crater, and from this the actual height estimation can be also done correctly. And this was used for landing on the South Pole, both from Chandrayaan 2 as well as Chandrayaan 3, even though Chandrayaan 2 actually the lander crashed while landing, but it was actually used in the same way. So you can see actually the nice small craters as well as the large craters, and how a craters, what you call the debris have formed and created a small mountain around it. Most importantly, how the sun's shadow is there. What I said, that 12-degree angle, that will effectively come out. The sun's shadow and the sun is shining on one face of the crater. So that tells you the quality of this image. So the PMC was mounted and it has generated volumes and volumes of data. For those researchers who are interested, they can contact ISSDC. ISSDC is the repository of our space, what you call ISSDC data center. You can register as a scientist and they can allow you to access the data actually. So this was a 3D view of the crater near Lindbergh. Here one thing I will tell you in advance, that the DEM generation is actually done in software. The camera itself does not give you, camera only gives you the data. The same way like a what you call अपना social media पे आप देखते हैं ना, people say that if you put your eye on this at some point, then you will be able to make it 3D. So the same way actually you have to see you have to actually 3 to a stereogram, then you can actually see it. But the image is, if the same image was seen through that one eye with a red and another eye with a blue, what you call our spectacles as is given in a 3D for cinema, you will actually make out the moon in 3D. Okay, now 3D view of the other certain areas I am showing you actually. So the difference between moon imaging and earth imaging is that the moon does not have polar sun synchronous or something like that. The orbital control on moon is very difficult maintaining, and hence the resolution may be slightly varying as well. But the important thing is our Chandrayanas which have gone spacecraft, they had excellent orbital control, and they were able to, the moon is having very much slight differential gravities in different parts actually, because the exact shape is not like exactly like the Earth actually. And but however, the orbital planes were maintained very accurately. And in the case of elliptical, then the satellite data which we get from these sensors is rescaled back to the required resolution. So this is DEM generation from TMC. These are other views. These are also what is called semi views. Here in mapping camera, you can see that you are able actually able to see the particular high resolution, how much resolution you were able to get. As a matter of fact, the TMC has mapped the entire moon several times over. There is an annotation also which is there from the altitude of 4,374 kilometers it has taken, because the orbit is elliptical. It's not so comfortable for a sensor as we could see from the Earth, where it's always having an equal distance from the Earth surface. Now I will come to the OHRC, the onboard high resolution camera, which was there on our Chandrayaan 2. And this was specifically made for finding out very, very fine details of the moon. Incidentally, it's a I will say sort of part of the story that we can see the moon at a higher resolution. ISRO can see the moon at a higher resolution than it can see the Earth. The best sensor we have on Earth doesn't see that resolution as the OHRC sees. Okay, more or less it can see at even 25 centimeters. So onboard high resolution camera. Here again, I have a exposed what we call 3D CAD diagram here, which is available in public domain. So this is again, as I said, the mirrors have to be folded and the light has to be sent back. There are several other folds inside also which are not seen. And so that the entire optical path of the telescope is reduced. Otherwise, you can't mount it on moon, because weight reduction is most important in moon, because you can't carry so much weight to the moon. Our rockets are not that large. So again, you have a secondary mirror. Most importantly, the moon materials which are used are very rigorous, because the moon temperature excursions are very high. An interesting thing was the baffle. The baffles are not required generally on Earth because of the stray light is less. But on moon, the baffle is required for this before the secondary mirror actually, to prevent the what we call the non-directional type of reflections coming back from and forth from different or specular reflection coming. So these baffles were introduced. Then you have DHA, which is the detector handling assembly, and the electronics cards which are put on these boxes. And you will see that each box has this hexagonal type of structure to increase the strength. In space technology, all the mechanical things are never made from sheet metal and welded. You have to see that the how we make the boxes are that we first have a huge piece of metal. From that, the unrequired part is actually etched out. There is with a actual CNC machine or a laser machine, we etch it out and leave the rest of the material which is actually required based upon a predefined method or the predefined areas which are to be there. And the best structure which has been found in all space technology is the hexagon. So with hexagons, the hexagonal structure will be effectively like the struts. So you can see this green line, the brown struts are there. Then the radiator. So for the detector and the electronics, which will heat up when they are working. So detector has to be kept cool. It cannot become hot, then its noise performance will go down. And the electronics, once it heats up, you have to cool it down. Otherwise, it will stop functioning beyond 55 degrees centigrade. And generally, we keep it joined at approximately around, try to maintain a good temperature of between about 40 degrees centigrade, 35 degrees centigrade, as cool as possible. Sometimes we even try to maintain in some of the sensors 25 degrees. The radiator is pointing to null, and that's the only way to leave the heat out. So this radiator, I showed the radiator in the INSAT also. The INSAT also has a huge radiator which will throw the light, and the radiator itself will get cooled to near null temperature. That's the deep space temperature. And from that, again, from that cold plate, the heat will be generated through electrically, and we will bring it back again to the actual temperature at which we want to use it actually. The electronic cards are on two sides, the green box and the red box, and the mounts which you are seeing, those 2 bolts and 4 bolts, that's how the payload is mounted to the spacecraft. So this is a blowout diagram. And here again, we have the photographs of the very high resolution. One very classic photograph was taken of the Eagle spacecraft of Apollo, which was seen and accurately seen. That's why I said that we are able to see the moon with very high resolution compared to what we can see on Earth. We could see with such a high resolution that we could make out the spacecraft also. As a matter of fact, our own Chandrayaan 3 landing site was also viewed, but that image I could not get over here. Okay, so close up view of the lunar surface by OHRC. Last photo here. Lunar surface by OHRC. This is Chandrayana 3, Chandrayana 2 photo. And you can see the type of what we call even individual boulders which are lying on the moon surface. They have been able to be made out so accurately. So, and the details of the photo have been given as well. So this is the last slide. And I think I overshot the time by 16 minutes. So, but the audience has not left. So that is good for both myself and Propagation Institute. So now we will have a 2 minutes break, after which I'll take a bit of water and then I will try to answer your questions to the best of my ability.
Yeah, thank you so much, sir. Just have water and just take few rests, sir, little bit, because I think lots of people waiting for asking the questions. They're excited for the questions. Okay,
Okay,
everyone.
fine.
So let me just tell you, there is a lots of question in the chat box, but I would just request to all of you, if you have any query, just raise your hand, everyone. Just raise your hand. I would just unmute yourself, like you people, and you'd be able to ask the question. Okay, everyone, just raise your hand if you have any queries. Okay, sir, as like they are taking few times, so let me just start because there is a lots of question in the chat box. So let me start from few questions. So basically, so there are some career related question also, sir. So should I go for the career related question first,
I
or
think we will make them wait to the end, right?
yeah, career
Yeah, yeah.
related things should be
What will happen is that if you answer the query first, then the technologists will also leave very quickly. So
uh,
let us take the technology first.
okay, okay. So basically, there is a lots of different, and there have been everyone just put there about the career related question because lots of people
Okay.
having a lot.
Okay.
Okay, so
Okay.
Atupa Bora.
Just read out one question, career related. Okay.
Okay, okay, so let me just read out few questions. So basically, there is a Mansi Pare, and she's asking, I'm an AI ML domain intern, so how I can get opportunity in the ISRO in the same domain to innovate and the problem solving for ISRO?
AI, ML, machine language, and artificial intelligence. Uh, See, there is that type of extreme specialization is not exactly advertised. So what generally will be advertised will be computer science and image processing, and this is one field in which the AI and ML, both machine learning as well as artificial intelligence, to generate a better quality from the existing images. That is what is done. The second field is where of the field of SATCOM, where there is a concept of utilizing some sort of a machine learning process to understand the type of noises which can come, or the code breaking or code making type of thing, AES encryption. So these are the two basic fields. However, specifically, uh, I'm doubtful whether ISRO would be advertising a specialist for AI/ML at their entry level courses. Actually, the general concept would be a computer engineering or computer science.
Okay, okay, sir. So now I'll go for the technical questions. So the question is from Atupa Bora, and Atupa Bora is not from India, sir. And she is asking about asking like, when you mentioned the corona in the space, so does that refer to an electrical discharge in the space? If so, could you explain what kind of discharge it is? It's a like wave
No,
based
no.
or something
No, no,
else?
no. No, it's,
It's
it's
not.
not like that. You see, the Bhaskara had a television camera which used to operate about 10 kilovolts actually, because it was using a what you call a TV tube actually for generating the image. Okay, let me tell you that even the Apollo cameras were actually TV cameras actually. So the television cameras in those days made used to make use of the electronic scanning, the actual electron, that reverse of your our tube television used to be used. So the electronic beam would be scanned and that would be registered. Now these used to be what is called the 10 to 12 kilowatt type of a what is called tubes were there. So when you take something to outer space and there is a vacuum, the outgassing happens. So along with the outgassing, the corona, this has got nothing to do with space corona. Within the satellite itself, sparking or a huge corona happened, and as a result, the TV tube itself has gone bad.
Okay. Yeah. Okay, sir. Yeah.
It's,
So,
it's called corona in terms of the failure methodology.
okay. Okay. Is it related to the sun flares, whatever the sun flares
No, no,
coming,
no,
sir?
no, 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 no,
Okay,
no, 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 no,
not that one,
not at
right?
all. It's actually we were still in the process of learning. Actually, let me tell you that even in the earlier what we call the NASA flights which used to be there, the cameras which they used to make with the tube cameras, there have been failures in the high voltage section which used to provide the electrical scanning because it used to be very difficult to make and especially creating the ceiling and which would work at such a high voltage. So it has got nothing to do with solar corona actually.
Okay.
The
It was
corona was the
man-made.
actual the corona has happened within the satellite. As a result, it is sort of effectively sort of that part of the satellite has burned down.
Okay. Okay, sir. So there is another question by Chitra Mondo, and he or she is asking like how corona discharge tube used in the space, like how they are being able to use.
No, no, no. That now nobody is using corona discharge. Those days it was a compulsion that if you want to take images from space, the only camera available was because there were other cameras were film cameras. Okay, so there was there's a spy program of USA called the Keyhole. That's a very famous actually. You can read about it in Wikipedia. So they used to have film return. Film would be returned. All these type of digital detectors were not discovered in the 1780s at all. So the only way to take images was through the effectively the same TV camera which used to be working with the very large, huge electronic scanning, electrical or rather the electron beam scanning. The electron beam scanning itself was a very high voltage system. So that is how, that's why in those Bhaskara 1 and Bhaskara 2, those cameras were available to us. Okay.
Okay.
Now
Okay.
nobody is using it.
Okay. So basically, they are not using that right now. Okay, sir.
No,
There is
now we
another
have
better
solid state
question.
device.
Yeah. So there is a better question now. Yeah, by Yasika Saxena, basically with Yuraz. Yuraz have been also added a few questions in it. So basically, Yasika is asking, sir, please describe IRS 1A and 1B. The color channel is shown assigned different colors, like the green channel assigned to the red band and the blue channels are assigned to the green band. But how so? Is these colors assigned on the basis of spectrum of sun or what? And with that, Yuraz is adding that why did we simply not have some colored picture instead of red or the green or any other colors?
See, the entire practice of the remote sensing application specialists. This is not it. Let me tell you one thing. The satellite is not creating any red color image or any blue color image or gray. All the bands are only giving us gray levels. That is basically a bitmap. Okay. In the case of IRS, it was a 8-bit bitmap is what you are getting. All images are in grayscale. It is our interpretation. If somebody wants to interpret red color as a green color, then he is free to do it. You can create a color as you like. However, the false color composite, what I showed, it is based upon the practices of the remote sensing applications community, how they describe the features on Earth. And it is the universal concept. It is called the standard FCC, small s FCC. You can search for it on the web. So based on that, the vegetation is always shown. Green color is shown in red in satellite imagery. Then the rest of the colors are mapped accordingly based upon the bands of the satellite. Primarily, the vegetation is always shown in red. And by showing the red color, I don't know why they have decided. We can find out these actually started way back from Landsat. 1970s when Landsat, the remote sensing applications community, decided that green showing in red was the best way of doing it. And they used to map that particular. So basically, you may say that we are assigning three different gray levels to a R, G, and B composite. Okay, R. See, right now you are seeing my color. My shirt is blue.
Okay.
So the
Okay.
sensor itself is creating RGB. But in the case of satellite, the sensor is not creating RGB. So each band is separate. R is a separate grayscale of 256. G is a separate grayscale. Not necessarily G. G could be two Gs also. Two different Gs may be there. Blue is a separate color, gray band. Those three bands are separately transmitted to the Earth. On the Earth, in a computer, we are combining them as we like. So this is a methodology adopted by the remote sensing community and it is called the standard FCC, small s FCC, false color composite.
Okay. So basically, it's all about the RGB, but we are adding some colors into it.
No, no,
because
no, no,
we
no.
could be able to understand. Okay,
You are mapping a particular band to a particular color for our human
okay,
understanding.
okay. So we could just differentiate between all those things. We could understand
Yeah,
about it.
so that you can, so, no, no, another thing. So that
Yeah.
all the three bands you can see in one picture.
Okay.
Understood. So those
Yeah.
features which are coming on three separate photos. Otherwise, you would
Okay.
be seeing blue as a separate photo. Okay, you will have to see three separate photos. I'll have to keep, let us say, one mobile for blue, one mobile for green, one mobile for red. But because I merged all the three onto one band in a color band, so as a result, I can make out all the objects on one screen itself or on one photo.
Okay.
Okay, so it's merging.
Okay. Okay, sir. Okay, it's really nice. Okay, so the next question by Logesh Karan R is asking, what are the limitations of current remote sensing satellite in forecasting weather and the natural disaster like the landslide, floods, in the mountainous or the hilly areas, and how can emerging technology such as AI, IoT based sensor, and the high resolutions imaging help overcome these challenges?
Okay, this is a good question actually from the applications point of view. It's a good question. But the point here is that prediction is one part of his question, and second is the mitigation is the other part of the question. So right now, the role of satellite based remote sensing is more on the mitigation side. On the prediction side, people are able to find out and have predicted that if a particular glacier has moved in this sense, or if a particular ice buildup has happened in a particular thing, and those data has been acquired and processed in time regularly, then, for example, in some cases, while dam bursts have happened in the Himalayas, in other cases, dam bursts have not happened because people have been warned in advance that the ice buildup or the water buildup has happened already. And as a result, it is time for you to release the gates. So satellite data is preventive in some cases. However, for this, especially for high resolution imaging, we need a much bigger constellation of imagery, because right now our revisit time, that is, you are able to visit the same area after 5 days, 6 days, 7 days, depending upon the orbital mechanism. So if we have a the what you call the eccentricity is such that the orbit is, we are making 14 orbits a day, so the entire globe will be covered in certain n number of days depending upon your swath, and after that you will have the revisit. So the revisit time being low, you can get the time series of images. From that time series of images, there are applied scientists, geologists, hydrologists who are carrying out such images. If you see the Indian Society of Remote Sensing journal, you will see our LCVAR journal, then all types of remote sensing, you will find that there are some people who have already started predicting. Then the second part of this, but however, I agree with him that you require a first and foremost geological information below the surface, other than through the radar images, which can give us information about subsoil up to few centimeters or at best up to a one third of a meter or so. Other than that, penetrating the earth with a satellite data is not possible. You are only able to get the reflected light in electro-optical sensors or the earth observation satellites. So getting data from below the earth will require what is called corroborative data. So if somebody says that, okay, from the surface I have seen a fault, somebody, let us say, has seen a earthline fault, that, okay, geologically I am seeing a much wider fault, it has become wider, or the fault line has now seen in some other parts. So for example, cracks in some of the our Uttarakhand, certain Uttarkashi area have been actually seen by satellites, and they have predicted that now it may happen in this path, so you should not build the road over there. But whether somebody listens is a different matter. The scientist has to tell. So it is possible to do it. However, it is not just resolution which matters. Let me tell you that resolution, if the resolution of data is very high, it will only give you a higher accuracy. But intuition and observation is also required. This is here the previous question of AI ML comes into picture. That pattern recognition using machine learning is very important, and in finding out additional information which a human analyst is not able to find out. A machine analyst is able to find out. So this is very similar to our medical analysis also. The robotic data analysis, for example, finds out tumors, finds out different type of diseases inside a body from a MRI, which a doctor is not able to find out. This is also happening both in CT scan and everything. So same thing applies to satellite data. So revisit times have to be improved. That is one thing. Second, for for such thing, we need a higher resolution hyperspectral. I have not covered hyperspectral today. Actually, I have covered only up to multispectral. Hyperspectral means that you slice our general visible band into 256 bands, or you slice it into more than 128 bands, or even 512 bands, 1 nanometer, 2 nanometer each. It's a different type of technology, and it requires and the resolution is, as of today, hyperspectral sensors, we have a lower resolution. We do have high, we call it HYSI. They have been flown. I have not covered it today actually. So this is about the remote sensing part and the feature identification. So far as the weather meteorology is concerned, our risk assessment, for example, the entire cyclone's landing point is exactly predicted by satellite data. We already have generated. ISRO itself has given the entire pack. I used to be one of the in charge officers for our National Meteorology Center, from where you are seeing all the images every day. So INSAT, and it's not that I have only worked in INSAT. I have worked in ISRO. Every engineer works on at least 5 to 7, 10 projects. All projects working in my entire department, I have to work in all of them. वैसा नहीं होता है, और हमारे वहाँ बिजनेस मैनेजर भी नहीं होता है. हमको खुद को बिजनेस मैनेजर बनना पड़ेगा, खुद इंजीनियर बनना पड़ेगा, परचेज भी संभालना पड़ेगा, एडमिनिस्ट्रेशन भी करना पड़ेगा, और रात को जितना काम है सब काम दिन का हो जाने के बाद रात को बैठ के टेक्नोलॉजी करने का. बरोबर, वैसे काम होता है. So ऐसा होता है. So weather prediction from satellite has created a considerable improvement in our own assessment in India itself. It has been heavily benefited. I will give one straight example here. The Odisha cyclone of 1979 lost more than 40-50,000 lives. And the same cyclone which happened recently of a even more higher power on Kutch, there is almost zero loss of life. Similarly, in the same Odisha, there is almost zero loss of life. The collectors and everybody are informed. Sirens go out more than 48 hours, more than 72 hours in advance. The evacuation starts, because we know the exact landfall point. If somebody says the landfall point is happened to be happening near Balasore, somebody says the landfall point is going to happen between Bhuj and Nalia, it will happen exactly like that. We have the software, we have continuous analysis, and we know exactly which satellite, which cyclone is going where. Heavy rain analysis is, and second important thing is INSAT is generating image near real time. Immediately, as like today, right now, you can see the image, night image. You can know exactly where the clouds are. And so subscale, they call it subscale actually. District level mapping is also available. So, and if we can make a even higher resolution, you can go to even higher subscale, but prediction wise, it will be an overload of data for the meteorologist. So we are, you may say, at a world-class level. India itself and the technology across the world is also at a world-class level. There is one more thing. People may say that whether nowcasting is not happening in India. For example, people feel that in UK or in USA, people will say that within 1 hour there will be rain. But that is very difficult in India, because it is much easier to do nowcasting. It is called nowcasting. Nowcasting in temperate regions is very much a very old technology. But the atmospheric dynamics in the tropical region is so different from that. You see, it is so different. The dew point changes happen so fast and so different that you cannot. So the algorithms for them are in the process of development. The data is already there. That I can tell you.
Okay, sir. I think it's a detailed explanation on that. Okay, so the next question by Harsh Nema is we can automated the landing system to the lander by using the images data through ML algorithm, but they are only north side data images which is not completed.
I couldn't get there. What's
They are talking about the moon, the north side.
Second part क्या बोला आपने?
Basically, he is saying is we can automate the landing system to the lander by using the images data through ML algorithm, but there are only the north side data images which is not completed. I think the question is not completed.
When we were landing, actually only the location was identified with the what data which I showed. That is the whether the overall general area is fine or not. So the AI ML was actually not used in that. Let me tell you, the actual live, the landing hazard camera, the lander camera, they were all live giving the data, and at that time it was an in-loop correction, which means the lander is actually telling. The lander is being told by the actual live cameras mounted on the lander looking at the moon surface that, okay, it's not good to land here because there is a rock over here. You change the thruster in such a way that you shift to the left or shift to the right and you slowly land. Okay, that's a live in-loop camera system. It's like your now automated driving system of your cars. So see, there is an obstacle in front of you. So you move to the left, move to the right, okay, or move to the brake now. Or now the road is clear, so you can drive fast. So exactly like that, a fully automated program was made. The Chandrayana 3 and 2, what you call the entire lander cameras, the lander hazard detection camera, and the what you call the ranging cameras, then the rover imager cameras, all these cameras were also made in my same department. I was part of the same department actually. All LI, MI, all cameras were made. So these cameras were connected to a set of microprocessors on loop. The code was on the box itself. This was not coming to Earth. From moon, the data takes 1.2 seconds to 1 second to come to the Earth. It is 3.6 lakh kilometers. So the light, that is the electromagnetic wave, will be 1.2 seconds. After you correct and calculate on Earth, send back, it is 2.4 seconds. So within 2.4 seconds, your lander will crash. You see, you can't do that. It has to be live in situ and in loop correction.
Okay.
So this is actually an image-based control systems algorithm, image-based live geolocation control, or rather lunar location control algorithm, which was implemented.
Okay. Okay. So instead of using those landing camera, if it be going to use another camera which is just orbiting or somewhere, so it won't be able to land safely. Because we
No,
just
it
need the
won't be able
instant
to
data.
land safely. It won't be able to land safely for two reasons. Because the camera which is there has to again send the command live to it, and that orbiter has to be always in view angle of the actual lander. You have to understand the orbiter is orbiting. So you need an antenna which is gimbaled. It has to point at that. And then that's a too much complicated system. The lander has to have an antenna which is pointing at the orbiter all the time. And while landing, you can't have that gimbaled antenna mounting and everybody looking at each other line of sight. You see, that's very difficult. That's much more complicated than what has been done as of today.
Okay, okay. Yeah, sir, I got that. Yeah, I think this doubt will be clear. So someone is asking, what is Nadir, sir? Like NADIR.
Nadir
What
is
is the importance?
looking to, if you are standing and you see the sun on top of you and your shadow is zero size, then the bindu point where your shadow is called nadir. If you are standing, the point on the earth surface which is exactly below, that is the yaw axis. Yaw axis is passing through the nadir and the null. Null is the deep space point where the yaw axis is going, and nadir is the yaw axis point where the earth surface is actually what you call is something like this is the earth surface. So the satellites, what you call central axis, is looking down. So that is called nadir. These terms are
Uh,
used in astronomy also.
okay. Okay, sir. Like I have a very different type of question here. You can see Tanishq Desmukh. He's asking how to build own ECU from own for own satellite and the rocket. Will Mega Arduino can be used?
By ECU mean that automotive engine control unit? Ask him.
Tanishq Desmukh, if you are here, just turn on your mic and ask right now. Tanishq, am I audible?
No, because a satellite has several of such what we call a bus management unit, then the attitude and orbit control system unit. These are all automated microprocessor based units actually on board. Then the payload controller unit. Yeah.
So basically, Tanishq is asking about the rocket propulsion system, sir. Tanishq, can you just unmute yourself and ask directly? I think that would be way more better. Just unmute yourself and ask. Tanishq, am I audible?
No, no problem. I will answer him. The rocket actually does not have one control system. Hello. The rocket has a master attitude and orbit control system. It has one master attitude and orbit control system which sits on the top of the rocket, and it controls the what you call the vector thrusting units. Okay, so which maintain the attitude and orbit of the entire rocket. If he's talking of the rocket, and these are always in main redundant. These are always in several types of main redundant control, and this is mounted in the last stage. Okay, so the wires reach from the bottom, and each stage also has its auxiliary control systems. And these control systems are too complicated, and it requires several hours of talk actually, because they are part of the combustion system as well as the what we call the propulsion system, combustion system, and the Earth's what you call dynamic system, as well as maintaining what is called the dynamic center of gravity also. So everything is done by that control system actually, and it shifts the weight around, it shifts the fuel around, and it's very difficult to do actually. It's algorithms are very, but however, let me tell you that the entire control system for all our rockets, there is no import. Everything is done in India.
Okay. Okay. Tanishq, I hope your doubt would be clear. And if you still have any doubt, you can just unmute. And if you're not going to unmute, just type in the chat box. Okay.
He is
We'll go
talking
through.
of the satellite part, then let me tell you that the basic satellite has several such control systems actually working. There is no one single. But however, the major satellite or spacecraft control system is what we call the AOCS, Attitude and Orbit Control System. Then the Attitude and Orbit Control System is actually a full in-loop sensing plus A, and it controls what you call the wheels, it controls the torquers, it controls the station keeping, and it is in loop with the sensors. The sensors like the star sensor, the sun sensor, the earth sensor, the horizon sensor. So all these sensors put together, they feed the data, and based on that, the magnetic what you call the wheels. Because all our satellites which I talked of are 3-axis stabilized, which means that their earth view plate is always horizontal. They are not spinning anymore like. Okay, they are not spinning, they are not spin stabilized. Stabilizing spin is much more easy. 3-axis stabilization means that you are a human being. Human being himself cannot stand. You see, you have seen people who are doing spacewalk, they keep tumbling around. Human being cannot stand because he has no gravity. But you effectively create a system which forces the satellite to remain EV plate, that is the payload plate. The payload plate जो पृथ्वी को देख रहा है, it has to always look at the earth. If it tumble, then look somewhere else, that you are done for. No use. Okay. So all remote sensing satellites, the attitude and orbit control system is very important. Similarly, there is a power control system which manages the batteries and the power, the solar arrays. We have the telemetry and telecommand system. We have the entire payload has a huge data processing computer system inside. Then we have the HK processor or the housekeeping telemetry processor of the satellite. And the final thing is communication controller. Plus we have also, so these entire, it's a huge distributed control. More importantly for Tanishq, you have to understand one thing, satellites cannot be repaired. You cannot bring them back a satellite. It's more costly to bring back a satellite than to build one again. And if a satellite fails, then it is gone. A huge amount of effort. It takes more than 2000 man years to develop one satellite even by ISRO. So all that effort is gone, money is wasted because you can't, it's not a गाड़ी नहीं है रास्ते का तो कि आप जाके रिपेयर कर दिया मैकेनिक को बुला के लाए. So every system which we have is main and redundant. Even the CPUs I am talking of, the entire systems, they are main and redundant.
Okay. Yeah, sir. But Tanishq has another question, and it is also one of the interesting one because he just want to do some projects. So is it possible to make working rocket for science project for me by using some microcontroller? I think yes. Yeah, sir. Just tell him.
Microprocessor and rocket are completely unrelated to each other. First of all, you require a
Microcontroller, sir. Microcontroller.
no,
Microcontroller.
microcontroller is actually a different point altogether. See, even if you have an analog control system, it will be able to control the attitude. Finally, the microcontroller is only controlling creating a program by which the control surfaces and the sensors data is accumulated. It is creating an algorithm and is doing the computation part. But you need a rocket first, na? पहले rocket तो चाहिए. तो आपको एक रॉकेट तो बनाना पड़ेगा ना. माइक्रोप्रोसेसर तो है ही, वो तो माइक्रोप्रोसेसर के बिना तो चलता ही नहीं है. बट नाउ हियर कम्स ए बिग डील. आई वांट टू टेल यू that the Russians were able to control rockets very accurately. In 1965, they never had any microprocessor. They used to use analog computers, and that too with valves. So sometimes we actually wonder how they could do it, and they could achieve exactly the same orbital accuracies which we are able to achieve even today, or the Americans achieved in 1970. So they were not having any microprocessors. Let me tell you that microprocessors were not even defined when rockets were already reaching into orbit. As a matter of fact, when Yuri Gagarin went, there was no microprocessor in the world in 1957.
Okay, these things were happen with the analog one. Okay, sir. So Gopika Naveen, the another question, and I think it's about the career related, sir. How is the scope of electronics and communication engineering in ISRO? How much rank is in the gate is required, and the ISRO exam should be one have to be safely assured that we can get the engineer in the ISRO. How is the interview selection? Basically, Gopika is asking about the career opportunity if she is pursuing electronics and the communication. Like what are the like pathways would be there, like after the completion of the bachelor's?
Okay. electronics engineering is one of the largest fields of recruitment in ISRO actually, and it's one of the core areas. So electronics engineering के लिए आपको you have to have a BTech degree. That is one thing. You have to clear the ISRO examination, which is the first level filter. And after you clear and you reach a particular percentile based on the number of posts and the number of applicants, the advantage is now it has become an MCQ type of question also. So the first level clearing now there may be, I don't know whether कोटा में institute शुरू हो गया कि नहीं ISRO में entry के लिए, तो शुरू हो गया है कि नहीं पता नहीं है मुझे. But the point is that it is possible. Previous year papers are also available now. So there is a learning experience is also there. You may say curve is also there. So after clearing the first, you will be called for an interview once you are selected. And uh, at the selection level, the type of projects which you have done and the type of interview which you give. And if at all you had a previous internship in ISRO or some other such other organization which is into hardcore technology, okay, it is into hardcore technology. If you just say that मैंने AI/ML का project किया है, but this that everything, but if it has to be substantial, that is one thing. And the electronics engineer having done some good projects, if at all you have published a bit of papers or something like that. So if you are so interested in joining ISRO, the best thing for you to do is to try first at an ISRO internship. If you have a 6 months, what you call last semester internship, then it is best for you. And even if you cannot join ISRO, let me tell you, a 6 months internship in ISRO would take you from a normal BTech degree to a very high degree, especially if you are going abroad or uh, joining even in a private company in India which is into designing development. That ISRO tag adds a lot of value to your degree. Okay.
Okay.
Hmm.
So there is another career related question, but
It's a
everyone,
basic government of India procedure. So you have to follow the basic government of India procedure, or rather we have to follow it.
yeah. So basically there is a lots of career related question only. So I'll just request you all, if you have any career related question, just turn on your mic, just raise your hand first, then I'll just allow you to ask.
No,
Okay, just
I'll tell you one thing. For all internship, you have to see the ISRO websites. Every center has its own website, and they will be it's there. And each of our centers has its own independent internship program through our HRD department. Every website you will go, you log in from the main ISRO website. You can go to the other websites, find out. Generally 6 to 8 months in advance you have to register through your college. That is the internship part. Job, it is a standard government of India job. It is as good as recruitment by any DRDO or anything like that. You have to clear the exam, appear for the interview. If you are cleared, then you are done for. You
yeah,
got it. Okay.
I think lots of all the center of ISRO already just keep providing the internship.
They keep providing internship. Yes.
Yeah, and they just launch their they just
But
release their circular and all.
there is no payment. There is no payment actually. You have to make your own accommodation. You can get a what you call very subsidized lunch, and they can help you out also if you are from if you say that in advance that I need accommodation, they can give you some single room accommodation also. Some of the centers can give, others not.
Okay. Okay, sir. So now we have another question. Basically, yeah, Tapan, just turn on your mic and you can ask.
Okay, sir. Thank you for opportunity for asking question. My question is that is there opportunity for physics student after post graduation to join ISRO?
Yeah, there is actually for physics student because we have several physics units actually. And if you are specialized in a certain type of physics, let us say material science type of, then or optics, okay, material sciences, optics, then what you call in astrophysics, there is a separate department, physical research laboratory. There is a space science laboratory at our Bangalore and SSPL, they call it. So there they have opportunities for physicists actually. But however, the engineering opportunities outweigh the number of physics opportunities. But there are physicists and there are also capability if you apply to physical research laboratory or to SSPL, then you can directly get a project also through them.
Okay, sir. Thank you.
Okay. Saurabh, next Saurabh, you can just turn on your mic and you can ask.
Good evening, sir. Thank you for giving opportunity to asking the question. Sir, I have a doubt regards, sir. After doing a MTech in CSE, sir, how can we apply for the internship or for the job in ISRO? And sir, second, my doubt is related to that, sir. Sir, how sir quantum computing or sir quantum computing can reduce the sir time between the that the delay which happen between the communication between the Earth and the Moon. So how sir quantum computing can reduce this? This is my two doubts.
I'll answer your first. The job part of it is what is that if you are MTech, actually there may be a separate recruitment at each center. That is one thing. So, but this job you have to. I am again repeating that these are all Government of India institutions. So, Government of India Department of Space is a hardcore central government body. So, the rules which apply to every department of Government of India apply here. You have to apply through advertisement, and only then you can get it. That is the only way. Okay. And ISRO is one of the organizations which does not allow entry by other means and all types of things like that. Now, so far as quantum communication is concerned, let me put the question back to you. Where in the world is a practical computer quantum communication available which is faster than the speed of light? Give me one example. Where
No
in the
sir,
world?
correct.
Where in the world is one quantum communication example available in practical prototype which is actually faster than the speed of light? Quantum communication is as of today only in theory. And quantum communication, if it happens, let me tell you, it means that you created a quantum communication means here is a spin coordinates, everything, and the same what you call quantum which exists here may exist 10 light years away or something like that. So these are all right now as of today in theories. I don't know when they will come out into practice or not. But the point remains that there is a no quantum communication actually happening in practice. People are saying that they have quantum computers also and all types of things like that. But whether it is the actual quantum communication or not, whether any practical example is there, because quantum communication means that you are transgressing basic Einstein's laws of light. Okay, your matter is no more matter. It has crossed E equal to mc square, and you are communicating in less than 3.6 lakh kilometers. You are going less than 1.2 seconds. Okay, so let us say you are going, maybe you go even in, let us say, 120 milliseconds. But then it means that you travel 10 times faster than the speed of light. But which is that material which can actually communicate? Because this is a real signal, यार. हेलो, मेरे को वहां से OHRC का इमेज पृथ्वी पे लाने का है, बराबर है? तो the electromagnetic wave has to carry that bits, digital bits ना, binary bits 010101 यहाँ पे पहुंचने का ना, बराबर ना? तो वो पहुंचेगा कैसे? वो क्वांटम का अभी मेरे को एक डब्बा बताओ, हम उसको बॉक्स बोलते हैं, ब्लैक बॉक्स. आई वाज शोइंग ब्लैक बॉक्सेस ना. Show me one black box which can quantum communicate 10 meters in less than the time light takes to travel 10 meters. Okay, theory and practice में बहुत difference है. मेरे को तो अभी वो आप लोगों का एस्ट्रोनॉमी वाले का जो ये क्या कहते हैं, once I had given a lecture once long back 20 years back in Doordarshan on Big Bang theory. Now I feel that this Big Bang and small bang, Big Bang, jo bhi hai, I don't know whether it really existed or not. It appears to be more, the universe is more like a, anyway, this has got nothing to do with ISRO, actually, it's my personal amateur astronomy theory, that the universe may be more like a quiescent condition. Everything is roaming around, something is happening, becoming matter, something is becoming dark hole, something is becoming black hole, something is becoming neutron star. And then again, everything is becoming again, coming back to what you call the excited state and becoming atoms, molecules. So we, as a matter of fact, are living in a world which is a macro world. You see, it is a highly energized world where everything is having a spin, everything is having a rotation, everything is having a charge. Okay, and as a result, all we are talking of is at the macro level. Engineering, etc., we are talking macro level. See, you are all from the science technology. When I speak to people in नॉन साइंस में उनको दो शब्द यूज करता हूँ, न्यूटन का कानून, फिजिक्स का कानून और स्पेसक्राफ्ट का रिक्वायरमेंट्स. ये तीन का अलग नहीं कर सकते हो. सम स्टार्टअप फेलो टेल्स मी हम एक साथ 200 टन का होटल ऊपर चढ़ा देंगे. 200 टन का होटल चढ़ाने के लिए 20,000 टन का रॉकेट चाहिए, तो वो तुम्हारे पृथ्वी से ऊपर चढ़ेगा कैसे, वो बताओ मुझे. Chemical combustion cannot take up beyond some point, you see, because you cannot generate that much thrust. Okay, so this is the point. These are all still in theory, but it's still a good thinking. Let us hope that by you reach my age, quantum communication is there. But then there will be a very serious problem, whether life itself will exist or not. That itself become a problem, as we know. You know, because your quantum will be existing somewhere else.
Okay, okay, sir. So I have my question from my side also. So as you just mentioned, like you just think very differently about the Big Bang Theory. So don't you support the Big Bang Theory?
No, no,
Don't you
no.
just feel like
No, 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 no. I used to, as I said, I have even given a lecture on Doordarshan in Gujarati language long back on Big Bang Theory. I, in those days, the amount of information was such that it was like this. Okay. But the point is that you are going on discovering older and older things or newer and newer things. And even people have started questioning whether the light is traveling in a straight line to you or it is traveling through a curve or through some gravitational waves or not. So sometimes I feel it's very different from this topic. Sometimes I feel how are you sure that a galaxy is which you are viewing at 10 billion light years away, supposedly light have something happened to it, it propelled to you faster or it came to you later, how are you so sure? It's more like that theoretical question which our young man is asking, that by quantum communication, light, maybe light itself has some quantum communication, it traveled faster to you and then suddenly turned into light again. It's possible.
yeah, yeah, sir. Okay, sir. So now we have Jia Srivastav. Just unmute yourself and you can ask. Okay, basically, she is working on some project and she just want to explain in front of you. Jia, Jia, just unmute yourself and go
Uh,
ahead. Yeah, just turn on
yeah.
your camera also, Jia, if you are comfortable with it.
Uh, okay. Sir, good evening, all of you, and thank you for giving me this opportunity. And currently, I'm working on a project that is based on NASA and ISRO dataset. So basically, my project is first of all astronaut fatigue. So I designed a model that basically trained a model that can deal with the heart rate of the astronaut and pulse rate and sleep monitoring and activity workload. So basically, it analyzes all the data and tell us that if the astronaut is in the working condition or not. If he having the alerts like sleeping disorder and heart rate variability, so it can generate the result. So based on that problem, after generating the result, I designed actually a beam my and actually my team will design offline functionality health issue. It is completely based on the machine learning and deep learning, and offline data set we are using there. So we have the smart copilot system, like we using chat gpt with the help of internet to asking our problems. So when in that I'm using the manual data that based on NASA and ISRO dataset and training the model. After that, we having the Morse code blinking. So basically, it help when there is panic mode or there is compression. Astronaut will not able to speak. So we have the blinking code. That through the blink, with the help of the blinking, astronaut to tell us what he actually wants to tell. And after that, we are working on the food and waste management system. So we are just in a space, and we have a unique loop that we can reuse the resources, like from the food waste. We can also implement the hardware from the with the help of the algae. We can make the oxygen from it, and we design that algae to grow in the darkness. So if we have the lack of oxygen or the oxygen level is come, we have just provide them the light. So there is a more so there is more growth in the oxygen level, like algae will work on 2x and 3x. And the second and the Harsh Nima is my teammate, and he already asked a question about the navigation and the backup landing system. We are gonna try to do this and using the machine learning model to train the data set. So, sir, these are all my projects, and there is a multiple schedule. Like we designed the psychological stress too for the VR environment, and it is completely based offline. Like astronaut wants to connect with their family, so he just uploading the image and videos of their family, and there is complete VR system that he can imagine. That he is with his family, and there's meditation activities like ocean views too, whatever he wants to do. So we are working on that project and training the model. And for the food and waste management, our main focus is for the urine reactor. We have to convert the urine reactor from urine to clean water. So there are two more phases in that. So we are working on this project. So I have to ask that what are the necessary data set we are using in it, and for the real world data, I want to some real world data from the ISRO. So can we have that data so can we can train our models, and there are many more suggestions from your side on this project.
I don't think I may not be able to access all the things because what you are talking of is lot of what you call specific biological processes. You may get some data from NASA, which is specific to them. I don't know even whether NASA is actually distributing such data. It may be a template data actually. Second important thing
Um,
is the theoretical simulation of all these type of things, converting the what you call the waste products to everything theoretical models in a computer using AI ML. Uh, these are hardly ever correlated with the actual practical technologies. So even oxygen conversion has been done by several people in different methods. Some people use calcium systems, some people use biological systems to do it and all types of things like that. So, and if you are using algae, your algae itself has to first survive. So simulating all these things. Second important thing is you said that you asking Chat GPT, but then Chat GPT cannot do original research. Let me tell you that Chat GPT can at best do a research out of some existing research. If you want to do something original, you see, ChatGPT is what? It is learning itself based on some other learning which is available on the public domain website. Like I have shown some photos available on public domain website. I myself may be having some other information about INSAT, Cartosat, but I have not put it in public domain. So how ChatGPT will learn? So ChatGPT is going to learn. So this one thing I will give a very general advice to people who are over here listening and to all other students. Don't be so running after AIML, AIML, AIML. See, ISRO will not be so much what you call impressed with your AIML at all, especially if you are working with Chat GPT and such things. We want real people.
uh, so
That is one thing. We want real people.
sorry to
No,
interrupt.
no, no, interrupt nahi. The way you have described to me, you are doing so many things. Please keep the focus on only one thing. If you are doing the biological health monitoring, don't do so many. You are at which level? BTech level or MTech level?
Also BTech level.
हाँ तो बीटेक लेवल में एक पक्का प्रोजेक्ट कीजिए ना तो if I am
Um,
recruiter I am not going to be impressed. I will be very frank with you, giving very harsh and correct advice. Do one
yes,
thing
sir.
and don't put. Okay. You see, if you are doing biological processes, study the biological, what you call the basic sinus rhythm of the heartbeat of the person. What is his blood pressure theory? What is the blood flow theory? What is the electrolyte level? These are all monitored as part of the what you call human spaceflight programming. I used to be one of the reviewers of human spaceflight, so we know all these type of things. What is the actual ambient carbon dioxide? What is the ambient nitrogen level? You see, I don't know whether you are aware of not. The amount of nitrogen is much more important than amount of carbon dioxide. If nitrogen changes, a diver loses his life because nitrogen enters the blood. You know what? Have you heard this? Divers cannot die beyond some point because nitrogen is the main problem. You have to maintain nitrogen in your blood. So nitrogen cannot be exceeding some limit. Then you have to maintain the oxygen pressure, what is called the differential pressure of oxygen. So all these type of things, you do one pakka project and don't focus on it, which you can do it and take it to a stage of completion. You start doing a urine remanufacturing into water and creating oxygen using algae. ISRO itself so far succeeded only creating चौराफली in space. तो algae जिएगा कैसे वो तो करने के लिए एक बहुत बड़ा डब्बा चाहिए. Well, NASA has done everything because NASA sent up the first space flight in 1969, more than now 55 years earlier. Okay, they have a lot of experience, but in between they also gave up. The International Space Station has already got what you call systems in place for this, but they don't disclose all these technologies publicly actually. So what you are talking is you are trying to combine everything real world on your computer screen, which does not happen like that. Real world is very different from a computer screen. And my request to you is that do not focus on too many projects in spite of having a team. Do one small 100% project in BTech. It is going to be much more valuable to you. And try to publish it in any paper somewhere.
Yes, sir. Sir, first of
ISRO,
all,
as of now, you can request ISRO, but I doubt if such a information is available because ISRO has just sent up people to space using some other companies' persons. Okay. So at best, ISRO also is doing in the process of simulation of data as of now.
yes, sir. Sir, there is one correction. I'm taking Chat GPT as an example. Like we are not using the Chat GPT. It's the model we are design a co-pilot system that astronaut can access it for to monitor or the related issue for the health, like offline system. So like we are using the chat GPT for our problems, so we can astronaut can use that system, like that co-pilot system name as health issue. So I'm taking it as an example.
Anyway, I think we can later on take it at one-on-one. Maybe I have not been able to understand your full problem because there is a physical world model, a biological world model, as well as the what you call the monitoring systems, the accuracy of it, and what model you are developing. So
Yes.
whether abstraction in terms of artificial intelligence is even possible in such things in real world or not, because a health issue is not generally addressed by artificial intelligence. Further, every biological human being different, you cannot generalize. That is also another thing. Okay, I think we will take a next question. Maybe we can later on discuss about your project at a different time frame.
Okay, thank you, sir.
Okay, thank you, Jia. Okay, sir. I think we'll go for the two more question, maybe. Uh, Yasika Saxena, you can just unmute yourself and you can just put your doubt, what the doubt you are having. Yasika Saxena, am I audible? Yeah. Yasika, you are not audible.
Yeah, I can take another question then.
Yeah. Okay. Yeah. By Chitra Mondal.
Sir, good evening, sir. Thanks for the opportunity for asking me the question. Sir, I am my one doubt is that how can that BSc physics student can do an internship with ISRO?
BSc Physics.
Yes, sir.
I am not too sure about how a BSc Physics student can join internship in ISRO. As of today, what I am aware of, BTech students in final year are allowed actually. But you can write to Physical Research Laboratory, and their HRDD department has a separate website. So there, I think the physics people may be able to answer in a better way actually.
Okay, sir. And the career
Yeah, you can.
opportunity at ISRO when it starts after BSc, after.
Our specific Master of Science projects do some projects sometimes actually, who are MSc students actually. And but if you have some good project, I think the correct answer would come from the HRDD department, depending upon your profile and everything like that. But one thing I will give a general tell you actually, that the your organization has to give you a sponsorship letter that you are recommending for this. That is one thing, and generally they will seek someone who are the first few percentile of the class and the batch. That is one thing.
Okay, sir. Thank you.
Okay. Okay, by Chitra. Sir, we'll take the last question from the Saurabh now. Will the session going to be end after that? Yeah, Saurabh, if you have any queries, yeah, just continue. Raise your hands. Just unmute
Good evening,
yourself.
sir. Good evening, sir. Thank you for giving me opportunity to asking my questions. As you very well explained me my previous questions, sir. Just I have two questions. Sir, my first question is that being fourth year student of a BTech Computer Science, sir, I have many fascinating things toward the research things, whatever I find like computer vision and NLP, and I find the solution. So, sir, being a student, how can I do the research, and if any solution I have, so how can I publish it? This is my question. Answer the similar related question is that, sir, like I have one, I just find the solution related, sir. Any aerial target, now we have a defense system, and sir, whatever the right now we have our defense system working on a classical computing system, and that's why, sir, we are unable to find the we are unable to neutralize any aerial target like hypersonic missile system, which are, sir, more than the twice the speed of the sound. I may be wrong, but sir, that's why we unable to neutralize them, because sir, our classical system has very less time of the window. But if we use the quantum computing, so we can quantum computing, and we integrated our computer vision system with the lidar and the sensor, so easily we can easily we can target, we can monitor them, and we can neutralize the target with the help of quantum system. So, sir, my question is that, sir, this type of the solution what I want to give. So, how can I convert this solution, my hypothesis, into the research paper? And sir, how can I develop my more view and more research people think. This is all, sir.
To do research on a what you call, if you have good ideas, I agree with you. It's good to imagine things. But there is one thing which I want to tell all of you here, that space technology and military technology, these are two fields, and medical technology. These three fields, they do not work on any imagination. You will be surprised to note that even all satellites across the entire world today, whether NASA satellite, ESA satellite, ISRO, JAXA, that is Japanese satellite, the telemetry transmitter, we are still using the 1978 CD4050, CD4051. You have to understand all these fields where higher reliability is required. You see, you cannot go and tell that I will do in medical science, like the lady was saying, I will go with astronaut, some artificial intelligence. ऐसा नहीं होता है. You have to first prove your technology. We use components which have a 5 years, 7 years heritage. They have to prove themselves for 5 years, 7 years. After that, they have to be hermetically sealed. In space, every technology, everything which you do, your algorithm has to be proved first on ground for several years. It has to run black box testing, white box testing. Theories are very nice. Okay, you made use of so many words. LIDAR से आप sense करेंगे, आप quantum computing करेंगे. But the point is that computing systems are never the limitation in military detection. Let me tell you, the amount of computing required in military systems is actually very less, because the amount of data being generated is not that high, except for the radar imaging satellites and the EMI EMC systems. Anyway, it's beyond the scope of this talk today, and these are all considered restricted technologies. So the amount of computing maximum which happens is in what is called the flight control computer of a unstable aircraft. You know that a Sukhoi 30 MKI is a basically unstable aircraft. It has to be forcibly controlled and made stable and made stable. For that, the computer requires a very lot of computing. Second, you cannot create such things into practical world so easily. You can remain in theory. आप क्वांटम कंप्यूटिंग कर रहे हैं, आपको वो फोटोग्राफ्स दिखा रहे हैं, गूगल ने ये बना दिया, उसने ये बना दिया, बट ठीक है, क्वांटम कंप्यूटर्स अभी तक दुनिया में प्रैक्टिकल साइड में आने के लिए देर लगेगा. That is the point. Okay. And secondly, again, I am requesting you all, see, imagination is one thing, but engineering is something else. You should be more focused in your approach. Try to select small projects and don't think that things are not happening, because see, United States of America is not using quantum computing, but neither Israel is using. They are using conventional computing, but they have rockets which can shoot down. But even there, they found a very difficult situation, that the number of shooting down rockets was outnumbering the number of incoming objects. So they were very costly. You see, people started saying कि $1 लाख का वो अपना स्कूटर का मशीन वाला वो ड्रोन को आप $1 million के रॉकेट से मार रहे हो, so फिर तो आप क्वांटम कंप्यूटिंग करके करोगे क्या? Practical world is, again, I am telling you again and again, practical world is very different from theoretical world. And do imagine, but at the same time, there should be a balance between imagination and the real life. And especially space technology, military technology, these are all related to technologies which are proven. You have to first prove 100%, then only they will accept it, because they cannot fail in operation. That is the more important thing. अभी विक्रम सीपीयू आपने देखा था, वो मिनिस्टर ने एडवर्टाइज किया था, that Vikram CPU is based on a very, very old microprocessor. Okay. So the high reliability is the maximum important thing. Medical science, defense science, and space science. These are the three fields. And again, one more field is there. That is what you call underground deep mining. Okay. So there also, if things fail, the persons will lose their life. So those few technologies are very crucial actually. Okay. So imagining things is one thing, but trying to create a project which is going to be helpful for you in the real world is more important for you.
Yeah. Absolutely, sir. Sir, I think it's the end of the today's session. There is a two last questions. Basically, there are two people, Yasika, and there is another one who is asking about they are pursuing the mechanical engineering, and the another one is the chemical engineering. So, is there any scope in the ISRO? Basically,
there is too much scope. There is too much scope in ISRO. Mechanical engineering is one of the largest recruitment in our entire rocket, satellite, everything. And everything which I described to you, Even in our electro-optical sensors, the mechanical engineer is the most crucial guy, because you will be surprised to note the electro-optical sensors which I described to you, they have the highest order of tolerances anything made by India ever. You have tolerances of the order less than 1 micron. Okay. The surface accuracy of a mirror is in the order of 1/8 lambda. So if lambda of red light is 700 nanometers, it is 1/8 lambda. उतना सरफेस एक्यूरेसी चाहिए आपको. वो इलेक्ट्रो ऑप्टिकल स्पेशलिस्ट, मैकेनिकल इंजीनियर सब लोग मिलके ही काम करते हैं. इट्स अ टीम स्पिरिट. एंटायर रॉकेट इंजीनियरिंग इज मैकेनिकल इंजीनियरिंग. एंटायर कंबस्शन इंजीनियरिंग ऑफ रॉकेट्स इज केमिकल इंजीनियरिंग. So these are two hardcore fields. So as a matter of fact, the number of engineers required in all these fields would be, mechanical would be one of the largest actually.
Sir, I think they should try to check out ICRB.
मैंने जॉब काउंसलर नहीं बनना है मेरे को ऑनलाइन में.
Yeah, I think they should check out the ICRB, right? Just go and check out their website. There is a lot of information.
Check the ICRB website. I used to be a member once of ICRB actually, electronic side.
Okay. Sorry, sir. I didn't mention that in the starting because I didn't know about it. Okay.
Yeah, for 3 years I was a member. So.
Okay. It's really nice. Okay, everyone. So this is the end of today's session. Just do one thing, everyone. Just turn on your camera so we could just capture this fantastic moment, because I didn't expect like this much people just going to come, because tomorrow is the Diwali, but still people are here. So yeah, everyone just turn on your camera. Everyone, please turn on your camera so we could just capture this moment.
Thank you everyone for taking all your time. It's been more than 2 hours actually.
Thank you so much, sir. Thank you so much to you, basically.
Thank you, sir. Very, very informative session. I am Devendra Kumar from Blunshahr, Uttar Pradesh. Thank you, sir.
Thank you.
Okay.
आप
Okay,
बहुत
everyone.
बढ़िया
So this is-